everywhere, but you will never see one. Trillions of them are flying through you right this second, but you can't feel them. These ghost particles are called neutrinos, and if we can catch them, they can tell us about the furthest reaches and most extreme environments of the universe. Neutrinos are elementary particles, meaning that they can't be subdivided into other particles the way atoms can. Elementary particles are the smallest known building blocks of everything in the universe, and the neutrino is one of the smallest of the small. 1,000,000 times less massive than an electron, neutrinos fly easily through matter unaffected by magnetic fields. In fact, they hardly ever interact with anything. That means that they can travel through the universe in a straight line for millions or even billions of years, safely carrying information about where they came from. So where do they come from? Pretty much everywhere. They're produced in your body from the radioactive decay of potassium. Cosmic rays hitting atoms in the Earth's atmosphere create showers of them. They're produced by nuclear reactions inside the sun and by radioactive decay inside the Earth. And we can generate them in nuclear reactors and particle accelerators. But the highest energy neutrinos are born far out in space, in environments that we know very little about. Something out there, maybe supermassive black holes, or maybe some cosmic dynamo we've yet to discover, accelerates cosmic rays to energies over 1,000,000 times greater than anything human-built accelerators have achieved. These cosmic rays, most of which are protons, interact violently with the matter and radiation around them, producing high-energy neutrinos, which propagate out like cosmic breadcrumbs that can tell us about the locations and interiors of the universe's most powerful cosmic engines. That is, if we can catch them. Neutrinos' limited interactions with other matter might make them great messengers, but it also makes them extremely hard to detect. One way to do so is to put a huge volume of pure transparent material in their path and wait for a neutrino to reveal itself by colliding with the nucleus of an atom. That's what's happening in Antarctica at IceCube, the world's largest neutrino telescope. It's set up within a cubic kilometer of ice that has been purified by the pressure of thousands of years of accumulated ice and snow to the point where it's one of the clearest solids on Earth. And even though it's shot through with boreholes holding over 5,000 detectors, most of the cosmic neutrinos racing through IceCube will never leave a trace. But about 10 times a year, a single high-energy neutrino collides with a molecule of ice, shooting off sparks of charged subatomic particles that travel faster through the ice than light does. In a similar way to how a jet that exceeds the speed of sound produces a sonic boom, these superluminal charged particles leave behind a cone of blue light, kind of a photonic boom. This light spreads through IceCube, hitting some of its detectors located over a mile beneath the surface. Photomultiplier tubes amplify the signal, which contains information about the charged particles' paths and energies. The data are beamed to astrophysicists around the world who look at the patterns of light for clues about the neutrinos that produce them. These superenergetic collisions are so rare that IceCube's scientists give each neutrino nicknames like Big Bird and Dr. Strangepork. IceCube has already observed the highest energy cosmic neutrinos ever seen. The neutrinos it detects should finally tell us where cosmic rays come from and how they reached such extreme energies. Light, from infrared to X-rays to gamma rays, has given us increasingly energetic and continuously surprising views of the universe. We are now at the dawn of the age of neutrino astronomy, and we have no idea what revelations IceCube and other neutrino telescopes may bring us about the universe's most violent, most energetic phenomena.